Good morning, dear students. This is next lecture in the course of geometric modeling. The topic of this lecture is relations. Today the following themes will be covered. We recall about binary relations, relations on a set, representing relations, and after that we will consider spatial relations. So let's start. Relationships between elements of set are represented using the discrete structure called a relation. Examples of relationships between elements of set occurs in many contexts. This is the set of employees and the set of their salaries, and flight numbers and takeoff times, students and subjects, and so on. Let us remind you the term Cartesian product. The Cartesian product of two sets, A and B, is defined as a set of all pairs A and B, where A belongs to set A and B belongs to set B. In the example, you can see how all possible pairs form the Cartesian product of two sets. This operation is also called the product set, set direct product, or cross product. Let us mention one more term important in digital computing, especially in databases. The set R is called a relation between A and B if it is a subset of their Cartesian product. Few words about binary relations. Let A and B be any sets. Binary relation R from A to B can be identified with a subset of their Cartesian product A and B. Relation can be written in such a way. It means that A is related to B by R. Here are some examples. Let's define a binary relation. First of all, we need to make a list of all pairs A and B. If P of x1 and x2 is a predicate with two variables, then a binary relation will be following. A binary relation R corresponds to characteristic function defining a subset R with true values. Here is an example. We are given flights and time. The Cartesian product will be the following set, shown on this slide. Let's denote a new relation, takeoff. It will be a subset of the Cartesian product, and image that it will be the following. Let's consider the second example. There are sets of student A and subjects B. The relation R is the relation of students who passed subjects. Let's remember, an order between pairs is insignificant, but order within pairs is significant. And there is a question for you. If the cardinality of the Cartesian product is 18, can you calculate the cardinality of the relation R? Of course, the answer will be 10. Here is a bipartite directed graph for the relation R from the above-mentioned example. This is not a function because for each subject there are several values, but in general there are function relations. A binary relation from a set A to itself is called a relation on the set A. Binary relation R on a set A is a subset of Cartesian product. Here is an example. The relation less Z can be defined as a relation on the set N of natural numbers. Let's consider another example. Let A be the set of numbers 1, 2, 3, and 4. Which ordered pairs are in the relation on the set A if predicates which defines the relation is A divides B? Right, these are following pairs. Now let's try to answer on such question. How many relations are there on a set of n elements? When we have a relation on a single set A, each relation is a subset of Cartesian product. The cardinality of this Cartesian product is n squared. There are 2 power k subsets of a set of size k. If the set of tuples to choose from a set from size k, where k is equal to n square, then there are 2 power n square possible subsets. So it means there are 2 power n square possible relations on a set of n elements. Let's recall the notion of function. Function from a set A to a set B assigns exactly one element of B to each element of A. We can represent a function explicitly by listing for each value A in the domain A its image B in the codomain B. That is, we can represent the function as a set of pairs A and B of a binary relation. Let's consider example of a function f of x is x squared and two sets A and B. On the bipartite directed graph, the mapping from A to B will be looks like as shown on this slide. So the relation R will be this following set. There are two general ways to represent n-array relations, with a list of n tuples and with a function from the n-array domain to true and false. And there are two special ways to represent binary relations, with a 0-1 matrix and with a directed graph. Why do we need the alternative representations? Is one not enough? One reason that calculations are easier using one representation, other things are easier using another representation. Matrices are appropriate for representation of relations in computer programs, but directed graphs are useful for understanding the properties of these relations. For representation a binary relation R from A to B by a 0-1 matrix M of size cardinality A by cardinality B, let I and j element of matrix will be equal to 1 if a tuple n and b belongs to a set of relation R, and this element equals 0 otherwise. Here is an example. There are 3 girls and 2 boys. The relationships between them are following. Joe likes Susan and Mary. Fred likes Mary and Sally. Then the 2 by 3 matrix representation of the relation likes between boys and girls is shown on this slide. There is special case of 0-1 matrices for relations R on the set A. Convention of this case is following. Rows and columns list element of A in the same order. Therefore, a 0-1 matrix is square, n by n, where n is cardinality of a set A. Here is an example. Directed graph or D-graph is a set of vertices or nodes with a set of edges visually represented using dots for nodes and arrows for edges. A relation R from A to B can be represented as a graph. Here is the previous example represented by D-graph. Let's consider another example of D-graph. There is a set A and relation on this set A means A divides B. This relation can be represented by 0-1 matrix and D-graph. Now let's go to further and discuss the spatial relations. Spatial relation R on a set of geometric object G can be identified as a subset of Cartesian product G by G, where G is a set of all subsets, geometric objects, of some geometric space, for example 3D Euclidean space. A binary relation R corresponds to a characteristic function defining a subset of all pairs with true values. For example, relation L1 parallel L2 includes all pairs of parallel straight lines in the Euclidean space. There are 4 groups of spatial relations. It's topological relations such as containment and overlapping. Next group is geometric relations with parallelism and orthogonality. One more group is metric relations, which contains distance between objects. And finally the direction relations with north of, south of, and so on. Now we will consider all these groups. Topological relations are defined using point set topology concepts, such as boundary, interior, and exterior. Boundary of a region consists of a set of points that separate the region from the rest of the space. Interior of a region consists of all points in the region that are not on its boundary. Exterior of a region consists of all points that are neither boundary nor interior. For example, adjacency relation means that two regions share a part of a boundary but do not share any points in their interior, also called meet or touch relation. Point inclusion relation can be written by such statement, where point P belongs to some geometric space big P, and if small g is a geometric object in some geometric space, then this point P belongs to this geometric shape big G. Also, point inclusion relation can be defined by a following binary predicate. On this slide, the topological relations such as exterior, interior, and boundary are illustrated. Exterior of the point set G is a set of points which are not contained within G. Interior of the point set G is a set of points P where P is contained within G together with some neighborhood. Boundary of the point set G is a set of points P where any neighborhood of P contains both exterior and interior points. For example, for lines, the boundary of a line consists of its endpoints. The interior of a line consists of all points composing the line excluding its endpoints. Point membership property is defined by a three-valued predicate, which is shown on this slide. This predicate is related to ternary logic operating with three values, and can be considered as defined by two binary predicates. Let's consider basic classification of topological relations. The first relation is disjoint, when boundaries and interior do not intersect. The second relation is contains, when interior and boundary of one object is completely contained in the interior of other object. The third relation is inside, its opposite term of contains, when A inside B implies B contains A. The fourth relation is equal, when the two objects have the same boundary and interior. The fifth relation is meet, when boundaries intersect but interiors do not intersect. The sixth relation is covers, when interior of one object is completely contained in the interior of other object, and their boundaries intersect. The seventh relation is covered by, its opposite of covers, when A covered by B implies B covers A. The eighth relation is overlap, when boundaries and interiors of two objects intersect. One of the ways to define the above-mentioned topological relations between point sets is four-intersection matrix. This matrix is defined on the basis of intersections between boundary and interior of two point sets A and B. Each entry in the matrix is either empty or not empty. As you can see on this example, the topological relation meet is represented by this matrix. There are 16 possible matrix configurations, but only 8 are possible for regions without holes. There are pros and cons for this representation method. It's simple and well-accepted method, but it does not distinguish between conceptually different situations, which are shown on this slide. All these three situations correspond to the same matrix. For resolving such above-mentioned situation, we can use different values for matrix entries. For example, number of connected components of the intersections can be used to distinguish first and second situations. Adding the dimension of each component would distinguish from third case. There is extension of four-intersection matrix approach. It's 9-intersection matrix. Nine-intersection matrix is used for description of the topological relations between point sets in terms interior, boundary, and exterior. Interest in the matrix can assume values empty, non-empty, or correspond to other properties, such as number of components and dimension of each component. Let's consider an example with these two polygons. On this slide you can see the values of intersection components for two polygons in nine-intersection matrix in terms interior, boundary, and exterior. The values of the intersection component dimensions are represented on this slide. Now let's consider distance-based metric. Distance between two point sets is defined as minimal distance between their points. If dist is a distance function and c is some real number, there are following possible types of relations. When distance between a and b greater than c, when distance between a and b less than c, and when the distance between a and b equals c. Finally, let's consider one more relation. It's direction relation. For example, if directions of B and C are required with respect to shape A, let's define a representative point A. This point defines the origin of a virtual coordinate system. The quadrants and half planes define the direction relations. B can have two values, northeast or east. Exact direction relation is northeast. Here is a list of references where you can find additional information about spatial relations.